you for introduction. Hello, namaste, konnichiwa, everyone. My name is Togo, and I'm from the University of Electrical Communications, Tokyo, Japan. This is my first time to come India, but this journey is very comfortable and very exciting for me. I'm very happy to be here, and I talk about my research. Truly an honor. Today, I'll be talking about a topic, regeneration and replication of the human body. It's related to the technology of prosthetic hand and human body mimetic robot. Let me start by introducing my university, the University of Electrical Communications, or UEC for short. UEC is located in Tokyo, Japan, which is about 5,800 kilometers away from here. While UEC is relatively small in size compared to other universities like Tokyo University, but we think the UEC is a unique and exciting campus. Now let's take a look at the outline for today's presentation. First, we'll begin by introducing the background of our research on human body regeneration and replication, and how we are approaching these topics through we call humanization robotics approach. Next, we'll share some of work on myoelectric prosthetic hands, which relates to the regeneration of the human body. And finally, we'll move on to the topic of the human body replication and present our research on artificial fingertips and various anthropomimetic robots. To begin, let me introduce the background of our research. Human body movements are incredibly diverse. While trained and skillful movements like those of Olympic athletes are certainly fascinating, but I'm particularly interested in activity of daily living, such as reaching towards the higher shelf. Here you can see videos of my children acquiring movement. My daughter, when she was 3 months old, she can run, reach and grasp objects without any specific instruction. And also, my son, he was 1 year old, he can step walking, of course, without any specific instruction. They are very cute, but for robotics engineers and researchers, this natural development of the children are truly remarkable. So, the big question when it comes to this human movement is, how does our brain control the body? The difficulty of human motor control is often illustrated through various parables. One famous example is the centipede dilemma. In this parable, a frog teases a centipede by asking how it knows which leg to move next. The centipede is overwhelmed by the question and finds itself unable to walk. This story highlights how difficult it can be to explain our own movements or motor control processes to others. Another well-known concept in artificial intelligence is Moravec's paradox. This paradox points out that while it is relatively easy to program computers to play chess or pass intelligence tests, it is far more challenging to give them the perceptual and motor skill of a 1-year-old child, like my child. So, despite the remarkable advances in AI technology in recent years, but this paradox remains true today. Here you can see the movies of the various humanoid robots movements. The video in the top left is from the 2015 DARPA Robotics Challenge, which demonstrates the difficulty humanoid robots facing performing humanoid locomotion in natural environment. However, the technological advancement in humanoid robotics have been remarkable. 6 years later, as shown in the top right video, the humanoid robot Atlas can now perform parkour like this video. I cannot do that. Additionally, with the recent developments in artificial intelligence and high-power brushless DC motor technologies in recent years, as shown in the bottom left video, we are seeing the emergence of powerful, aggressive, and high-performance human robots in commercial in the market every week. It's very surprising for the robotics researchers. But this said, it remains challenging for robots to move with the several same level of dexterity as humans. There are two major approaches to understanding human motor control. The first is the analytical approach, which seeks to understand the target through analytical methods. This involves measuring, analyzing, and creating mathematical models to explain human motor control. The second is the constructive approach, which aims to understand the target by artificially building a model of it. In this method, the model is constructed through trial and error. One analytical approach to understanding human motor control is through a field called computational neuroscience. When a robot performs a task, a computer receives sensor information, and computer processes it and sends commands to the motor to move the robot's body. Similarly, when a human performs some task, the brain receives sensory information, and the brain processes it and sends commands to each muscle and to move the human body. In this way, computational neuroscience approaches the mechanism of human motor control by drawing analogy to human movement and robot control. On the other hand, a constructive approach to understanding human motor control involves developing robots based on bioinspiration and biomimetics. Bio-inspired robots are designed to capture the functional essence of biological forms. A famous example is a robot hand inspired by adhesive capabilities of a gecko. And the human robot feet designed based on the window's mechanism of the human foot. Biomimetic robots, on the other hand, achieve adaptability by mimicking the biological morphology in their design. Robots that closely replicate the human musculoskeletal structure have been developed as shown in the left picture. While bio-inspired robots tend to be superior in terms of robotic functionality and performance, but biomimetic robots are better suited for understanding function of the human body. To understand the human motor control, we take what we call a humanization robotics approach. First, we developed the cyborg robots inspired by the human body. These bio-inspired robots are designed to extract and replicate specific functions of the human body. The bio-inspired robots we developed so can effectively substitute for the human body function. On the other hand, to better understand how the human body goes, we are also developing human body mimetic, so-called anthropomimetic robots, which fall under the category of biomimetic robots. This is aligned with the constructive approach. By applying control models derived from computational neuroscience to these anthropomimetic robots, and comparing the movement with that of humans, we can verify the validity of the human motor control model. This corresponds to the analytical approach. There is a reciprocal relationship between the bio-inspired robots and the biomimetic robots. The technical knowledge gained from bio-inspired robots can be applied to the biomimetic robots development, while new functions discovered in biomimetic robots can be translated into the bio-inspired robots. This forms the foundation of our comprehensive humanization robotics approach to robot development. Let me introduce now two major efforts related to human augmentation, which is the theme of this design workshop. The first focused on the functional substitution, which involves the regeneration of the human body. The second is functional elucidation, which centers around the replication of the human body. In the context of human body regeneration, we would like to introduce the myoelectric prosthetic hands we have developed. Specifically, we will focus on the myoelectric shoulder disarticulation processes designed for individuals with bilateral shoulder disarticulation, which is considered one of the most severe types of disability. And next, in the context of human body replication, we will introduce the barriers as a polymetric robot we have developed. Among these, we will primarily focus on our research on artificial fingertips, where we have successfully gained insight into their functional rules through a constructive approach. Now let me introduce our research on myoelectric prosthetic hands in context of the human body regeneration. First, let me explain what the myoelectric prosthetic hand is. In this illustration, you can see a boy reaching a ball with his hand. From a system neuroscience perspective, the information processing is thought to be occurred as illustrated in this figure. Visual information about the ball is received by eyes and sent to the brain. After the brain processes this information, and motor commands are sent to each muscle, leading to muscle contraction, tweak, and that generates a movement. If a hand is lost due to accident or something, the ability to generate a movement is impaired. However, the series of functions still remains. The information from the ball is sent to the brain processes this information, motor commands are sent to the muscle, and the remaining muscles can contract. So the information about the muscle contraction is then measured from the surface of the skin using a sensor. These measured signals are called EMG information, and the robot hand is controlled based on this EMG information. This forms the basic system of a myoelectric prosthetic hand. And various prosthetic hands have been developed based on the type of disarticulation. Here we define the disarticulation as the loss of a limb from the joint, and amputation as the loss from the middle of the bone. Depending on the type of disarticulation, different types of prostheses have been created, including finger prostheses, hand prostheses, and forearm prostheses, upper limb prostheses, and shoulder prostheses. Among these, our research group has focused on the research and development of forearm myoelectric prosthetic hands and myoelectric shoulder disarticulation prostheses. In this slide, we'll explain what myoelectricity is. Myoelectricity refers to the bioelectric potential generated when muscle contracts, and it is measured by amplifying electric potentials on the surface of the skin. This signal is called electromyography, or EMG for short. This video demonstrates a measurement of EMG during a grasping motion. The area circled in the red bottom of the video shows the EMG sensor. And the upper graph displays the time series of measured EMG, while the lower graph shows the short time Fourier transformation applied to it. So upper graph shows the time domain information, and the lower figure shows the frequency domain information. As you can see, EMG oscillations are measured when the hand closes, and the amplitude increases as the hand closes more strongly. We also observe that frequency bands with greater power differs between the hand grasping and wrist flexion. So now is close strongly, the amplitude is increased. And you can see the frequency domain, hand closing and wrist flexion and closing is different. So we can recognize the user intended motion based on the frequency domain data. Our research group has developed a system that recognizes user motion using a three-layered artificial neural network. This system extracts features from EMG data in the frequency domain, converted by short-term Fourier transformation from the measured EMG signal. We refer to this as pattern recognition-based control. The system is trained in advance with EMG data representing different motions, such as hand grasping, hand opening, and hand relaxing, as teacher data. The robot hand then moves based on the recognition results. By utilizing features in the frequency domain, we have been able to achieve 15 types of motion discrimination using only 3 EMG sensors. The UECE hand shown in this video operates using pattern recognition-based control. As explained earlier, the 3 EMG sensors are placed under black band. And based on the EMG information measured by 3 sensors, motion recognition is performed in real time to move the robotic hand, opening and closing. The robotic hand can move at 2 points, the base of thumb and the base of the forefinger. This myoelectric prosthetic hand is capable of grasping and manipulating a variety of everyday objects with such a simplified mechanism. We have also developed a more simplified version of the UEC hand for children. This prosthetic hand uses EMG signals from a single sensor and operates based on a threshold, allowing the user to simply open and close the hand. Thanks to its simplicity, it is very lightweight and easy to use, making it suitable for children to wear and operate. In order to promote the social use of myoelectric prosthetic hands, our research group has been working to have the prosthetic hand we developed registered in the Japan's ready-made parts system. The ready-made parts list is a catalog that prosthetists in Japan can refer to when creating myoelectric prosthetic hands or leg. Users can receive public subsidies or money support to purchase prosthetic hands from this list. To be listed as a component in the ready-made parts, a prosthetic hand must pass various clinical tests and be technically modular, not a single robotic system. Our UEC hand is also modularized as depicted in this figure. The UEC hand was officially registered in the ready-made parts system in 2018. Now, the users can purchase with the money support of this myoelectric prosthetic hand system. And also followed by a multi-degrees of freedom prosthetic hand and an infant prosthetic hand are also registered. Now let's take to this slide. As you can see, in Japan, several myoelectric prosthetic hands in market are already registered as ready-made parts and are actually being provided to users. However, a major challenge is the cost. These prosthetic hands are very expensive, which has become a significant barrier to the widespread adoption, especially when it comes to myoelectric prosthetic hands with multiple degrees of freedom, meaning those with many moving parts. The cost becomes extremely high. This makes it difficult for many potential users to afford them. Our UEC hand is offered at a very low price compared to other prosthetic hands on the market. Similarly, the price of the PIT hand, which is a multi-degrees of freedom myoelectric prosthetic hand that our group developed, is also lower. This highlights the importance of cost reduction in making these advanced prosthetic technologies more widely accessible. Now, next we'd like to introduce the myoelectric shoulder disarticulation processes. A shoulder disarticulation individuals is someone whose arm has been separated shoulder joint, making it one of the most severe forms of disability. Traditionally, shoulder disarticulation processes have included cosmetic shoulder processes, hook-type shoulder processes, and body-powered shoulder processes. However, these require the user to move the other remaining parts of their body to control the prosthetic arm by pulling the wire cable, which can place a significant physical burden on the user. In contrast, the bioelectric shoulder disarticulation processes operate an electrically powered robotic arm using EMG signals. This allows the user to control the prosthetic intuitively without the need for the compensatory body movement. Just like with the forearm prosthesis we mentioned earlier, the UEC hand, in the case of the myoelectric shoulder disarticulation processes, we use EMG signals measured from the trunk area and processed to the disarticulation site, the input signal. These signals are then processed by a controller, which generates the motion for the robotic arm. However, there are some challenges here. One major issue is that we need to control a robotic arm with very high degrees of freedom by using only low degrees of freedom input signals. Another challenge is that achieving intuitive control often requires long-time training. To address these issues, our approach was to first simplify the robot arm structure and control by limiting degrees of freedom required. We then introduced a learning-based control method to make intuitive control easier for the user. This photo shows the EMG shoulder disarticulation processes we have developed. That is a simplified type. The weight of one side of the system is about totally 1.7 kilograms, which includes the hand and the socket, which is actually lighter than the average weight of an adult male's arm. The process is designed to control several degrees of freedom, shoulder flexion and extension, elbow flexion and extension, as well as hand opening and grasping. With these processes, the user can reach a specific point within the workspace. For such time-frame movements, the user utilizes the robot's degrees of freedom, while for the horizontal frame movements, they rely on their own body's degrees of freedom. It's a characteristic of a wearable robot, so a user can easily move the robot system by their own body movement. Next, let me introduce the elemental technologies we use. To measure the user's EMG signals from trunk, we developed EMG sensors suitable for trunk. This sensor is made from silicone and conductive silicone, which makes it both flexible and waterproof. The robot hand itself is the same model as our UEC hand. The controller incorporates the machine learning function as UEC hand. The EMG data collected from the sensor is first preprocessed using a short time Fourier transformation. After that, we extract the feature values in the frequency domain. And finally, a three-layer artificial neural network is used to recognize the user's intended motion. In our developed system, we designed the control method as shown on this slide. We focused on the three types of user motion: horizontal flexion of the shoulder, lifting of the wrist, and the extension of the shoulder. EMG sensors were placed on the corresponding points of the body to measure these movements: chest, back, and temple. The prosthetic hand can perform 4 different motions: hand grasping and opening, and arm raising and lowering. These 4 motions are controlled using 2 EMG inputs from the trunk and the griping motions as a switch. Horizontal flexion of the user's shoulder corresponds to the grasping motion of the prosthetic hand or the raising motion of the robot arm. And the horizontal extension of the shoulder corresponds to the lowering of the robot arm or the opening motion of the hand. The user's motions involving flexor muscles, flexion movement, correspond to the flexion movement of the process, and the same applies to the extension movement as well. The twitching motion acts as a switch, changing the process's mode from mode 1 to mode 2, from mode 2 to mode 1, without affecting the user's actual body movement. This switching control, combined with the machine learning function in the controller, helps reduce the impact of noise and unintended motion. Since only the user's movements are mapped to the prosthetic movements, the user can intuitively control the process. These videos demonstrated our evaluation experiments to moving the ball. The video at the top shows the results from a healthy user, while the one at the bottom shows the bilateral shoulder articulation user. Both users were able to intuitively control the prosthetic using the trunk EMG signals. The figure on the upper right displays the number of ball movements successful. The horizontal axis represents the vertical movement or horizontal movement. And as you can see, users were able to move the ball one or more times on average in 1 minute. And calculation took about 35 seconds from applying the processes, varying the processes, and to completing the EMG learning. This means that our system allows users to pick up and place the ball without requiring long-term training. However, one limitation is that the operating speed is slow, making the movement time-consuming. Next, we'll present our approach to addressing the issue of reducing the manipulative load for myoelectric shoulder disarticulation processes. Here we are showing a system neuroscience diagram that illustrates the reaching movement towards the ball once again. If we carefully observe our hands when moving them and reflecting my own movement, it is well known that there is a generally time delay of 200 to 300 milliseconds between the visual information and the corresponding movement. However, when we reach the ball, we are able to do so very quickly. The reason for this is that our brain is constantly predicting both the movement of the ball and the motion of our own body. By relying on these predictions, we can compensate for the time delay and execute rapid feed-forward control of our movement. As demonstrated in the earlier video, let's consider a scenario when the user is carefully operating the myoelectric shoulder disarticulation processes while visually monitoring. In this situation, the entire system forms a very slow visual feedback control loop, which increases the cognitive load on the user. To address this, we introduced a subbrain that can process visual information from the environment in a similar way as the user observes the robot and surroundings. This subbrain is capable of monitoring external environment and the robot movement and user state. Since the subbrain, especially a computer, can process information faster than the human visual feedback control group, so it can eliminate the time delay. By delegating time-consuming information processing to the subbrain, we thought it may be possible to achieve a form of a shared feed-forward control from the user's perspective. Based on this concept, we developed a semi-automated control system by integrating a simple myoelectric shoulder disarticulation processes with the mixed reality or MR, or recently called XR device. In this system, the Microsoft HoloLens MR device serves as a subbrain, gathering visual information and tracking the user's head orientation. The total system uses several biosignals for control, including EMG signal, visual information such as depth data, and the angle of the user's head. The EMG signals are measured from the chest, back, and the temple as in the previous setup of the myoelectric shoulder disarticulation process. Next, let me explain the relationship between the user's motion and the system. The clicking motion is used to detect the target by the MR device. If the user centers the vision to target and click, the system identifies that as the target point to reach. After this, the system automatically switches to arm movement mode, where the shoulder joint of the prosthesis moves only when the user performs horizontal shoulder flexion. If the user relaxes, the arm stops. It's ensuring the voluntary control. During this time, the system automatically calculates the target position based on the MR device's data. Once the system determines that the target has been reached, it switches to hand operation mode, where horizontal flexion and extension of the user's shoulder controls the closing and opening the robotic hand. After completing the task, the user can detect a new target by do it again, and then the system returns to the arm movement mode. Here is the actual video. The top video shows the user's view, while the bottom video shows the movement of the prosthesis. In this demonstration, the user looks at the ball on the wall, then performs a clicking motion to target the ball. After that, by performing horizontal shoulder flexion, the prosthesis automatically moves towards the target position. Once the target is reached, the user controls the opening and closing the prosthetic hand through his shoulder movement. We conducted a comparison between the semi-automated control system and the conventional visual feedback control system. As shown in this video, when operating at a normal speed, 0.3 radian per second of the shoulder movement, there is a little difference in task completion time between the two control methods, like this video. From green target to orange target. Conventional system also achieve the task. But why propose system that corresponds in the highest speed? Highest speed means the 1.06 radian per second of the shoulder movement. It's a limit of the motor. In this situation, the shoulder moves at its fastest speed. The semi-automated control system allows for quick and vertical movement of the ball like this. In contrast, the conventional visual feedback control system shows some challenges, such as overshooting and undershooting the target, and more time for switching actions because they check the state of the process by visual information. Let me show the result. In the graph on the left, the horizontal axis represents the shoulder movement velocity, and the vertical axis shows the number of successful ball movements. The red line representing the semi-automated control system shows the linear increase in success as velocity increases. On the other hand, the blue line representing the conventional visual feedback control system shows the plateau, with a significant difference at the highest velocity. The graph on the right highlights the occurrence of the overshooting and undershooting the target. By the semi-automatic control system, the average number of these errors remained below 1 across all conditions, like the red band. In contrast, the traditional visual feedback control system showed more than the one overshoot or undershoot on average and linear increase with velocity increase, and approximately 3 occurrences of the undershoot and overshoot. These results demonstrate the effectiveness and usefulness of the semi-automated control system with growth, especially during quick movements. The simplified myoelectric shoulder disarticulation processes have had significant limitations in terms of available movement. So to address this issue, we are currently working on developing much degrees of freedom myoelectric shoulder disarticulation processes with the same range of motion as the human arm. In these photos, you can see the prototype, which includes the 7 degrees of freedom robotic arm and 2 degrees of freedom robotic hand. As demonstrated in this video, the system can be warmed on the body and the arm moves in the response to the EMG signals measured from the arms. This is because this is a demonstration. However, the current prototype weighs 2.2 kilograms per only arm, making it relatively heavy. We are also conducting evaluation experiments on the multi-degrees of freedom where it shows the disactivation processes using the shock test. The shock test is commonly used in clinical trials. The goal is to assess whether it can perform arm movements comparable to the human arm. As shown in the video, the process is capable of tasks such as moving a bottle and turning a paper, and demonstrating the advantages of increase of degree of freedom. Additionally, we have now focused on the reducing the weight of the hardware by replicating the aluminum body with CFRP and carbon fiber reinforced plastic and other lightweight materials. We have managed to reduce the weight by 0.6 kilograms. We continue to reduce the weight of robotic arms now. Okay, next we'll talk about the replication of the human body. Specifically, we demonstrate the mechanism behind improving human flexion grasping performance using the artificial fingertips, as well as our efforts in developing the various anthropometric robots. As we mentioned earlier in the research background, we are particularly interested in the mechanism of human motor control. For example, when we think about movement, what is the source of our dexterity? Let's consider the action of pinching a small object with 2 fingers, its fingers and thumb, as shown in this photo. This movement is called precision grasping. When taking an analytical approach to this motion, we try to model how the brain performs such precision grasping and consider the computational process involved. The image in the upper right shows the model used to calculate the fingertip forces when a typical robot hand can perform the precision grasping. However, even without these complex calculations, as demonstrated in the lower right, a soft robot hand can softly grasp a variety of objects. This suggests that the analytical approach alone may not fully explain the source of human dexterity. We cannot easily separate the roles of the brain and the body in these tasks. This is where the importance of a constructive approach comes into play. There are several approaches to exploring the functional roles of the human body. One approach is a simulation-based study. By building detailed mathematical models using methods such as finite elemental analysis, we can simulate the mechanical phenomena at the fingertips. However, physical simulations often struggle with such challenges, particularly when it comes to contact with objects and the deformation of soft materials and the complexity of slips and friction. Unfortunately, these are preciously the factors that play a crucial role in grasping objects with our soft fingertips. Another approach involves using cadavers. This method allows the highly accurate reproduction of phenomena as it involves the actual human body. However, there are significant drawbacks to using cadavers, such as ethical concerns, limited sample sizes, and the fact that tissue characteristics can change over time. A promising approach is research based on anthropometric robots. The robots shown in these photos are designed to closely replicate human musculoskeletal structure, whether it's through the robotic hands and the humanoid robots. These robots are developed with the goal of achieving human-like movements and helping us better understand the mechanism of human movement. Through a constructive approach based on the human body replication, we have developed various anthropometric robots to better understand the mechanism behind the human motor control, like these photos. These include robot models of fingertip, hand, wrist joint, joint capsule, shoulder joint, foot. To begin, let me introduce research on fingertips. The human hand has several morphological features that are advantageous for grasping and manipulating objects. In particular, for precision grasping of small objects, the tips of the index finger and thumb are primarily used. The bone at the fingertip is called the distal phalanx. As shown in the diagram on the upper right, the human distal phalanges on the thumb and the index finger have developed asymmetrical shape. They are larger on the side that makes contact with the object during precision grasping. For the thumb, this is ulnar side, and for the index finger, it is the radial side. This asymmetrical shape is a well-known characteristic in the field of morphology. Additionally, it is also known that primates which do not perform precision grasping tend to have more asymmetrical distal phalanges. Based on these morphological findings, we formulated the working hypothesis. The asymmetrical shape of the distal phalanx improves precision grasping performance. To test this hypothesis, we developed artificial fingertips as shown in the photo on the left. It contained 4 parts, a 3D printed distal phalanx, bone, and nail, along with silicone, skin, and subcutaneous tissue, as shown in the diagram on the lower left. We created 4 types of distal phalanx. The first is a normal pair, which replicates the shape found in the typical human bones. The second is a mirror pair, which has a reverse shape of the normal pair. The third is an undeveloped pair, where the less developed side is mirror. The fourth is a developed pair, whereas more developed side is mirror. The red box highlights the asymmetrical group, and the blue box shows the symmetrical group. These artificial fingertips were attached to the tips of the robotic hand, as shown in the photo on the top right, and were used to perform the precision grasping on the cylinder. We then measured the drawing force using a tensile tester. The figure in the upper left shows a representative time profile of the drawing force. We evaluated precision grasping performance using 3 metrics: the maximum drawing force, the area under the curve representing the work of friction, and holding time, which is the time until the drawing force reaches 0 again. The statistical analysis revealed that the symmetrical group performed better than the symmetrical group in terms of precision grasping. In particular, the mirror pair highlighted in the red box showed a significant difference. These results show that in our constructive approach, we found that the asymmetrical shape of the distal phalanx improved precision grasping performance. But why? So we think that the reason the asymmetrical shape of the distal phalanx improved precision grasping performance is due to the way it influences the deformation of the finger pad. When pressing the finger pad against an object like a cylinder, the asymmetrical bone shape causes a bias in deformation of the soft finger pad. The area that deforms more significantly becomes compressed, increasing the stiffness, which in turn leads to greater drawing force as a reaction force. So we think that the asymmetrical shape causes a bias of a deformation and resulting in the higher reaction force. So the precision grasping performance will improve. Next, let's consider the role of the human fingernails. In the debate on typical robotic hands, the role of the finger pad and the nail are generally considered as follows. The finger pad is thought to cushion the contact impact with the object and generate frictional force, while the nail supports the deformation of the finger pad. Previous studies have shown that the robotic fingers with soft finger pads can increase resistance by 96%. Additionally, the fingertips equipped with the artificial finger pads and the nails are known to have a a higher coefficient of friction than those of without nails. This raises the question to what extent does the presence of a nail affect the grasping performance, and what is the functional role of the fingernails? To address these questions, we use the actual fingertips we introduced earlier. Again, we created 6 pairs of actual fingertips with various conditions, with and without nails, as well as hard, medium, and soft finger pads. These fingertips were used to grasp a cylinder, and we measured the maximum holding force. The photo on the left shows the experimental setup, and the three graphs on the right show the results with the finger pads becoming progressively softer from left to right. Right is soft and left is hard. The experimental results showed that for all actual fingertips, those with nails demonstrate relatively higher maximum holding force than those without nails. And statistically significant differences were observed in all pairs except for the hardest finger pad. This aligns with the previous research, which suggests that the nails increase friction. However, it should be noted that the overall effect was relatively small effect. But what's particularly interesting is the experiment where we have the actual fingertip grasp a T-shaped object instead of a cylinder. In this case, we also found that for all fingertip pairs, those with nails exhibited greater holding force than those without nails. The increase was most significant with the softest fingertips like this three times. The difference is much more pronounced than in the cylinder grasping experiment. This result suggests that when grasping a T-shaped rod with soft fingertips that have nails, the mechanism, other than just friction, is enhancing pressure grasping performance. So what is it? The photo on the left shows actual fingertips grasping the T-shaped rod. And for reference, we also included a photo of a human finger grasping the same rod. As highlighted in red circles, both the human fingertips and the soft actual fingertip with a nail deform in response to the corner of the T-shaped rod, creating a geometric constraint. This type of constraint was not observed with the medium or hard fingertips. Fingertips were not deformed. Additionally, when the nail was absent, the deformation of the finger pad was not supported, so the non-geometric constraint was formed. This suggests that the interaction between the soft finger pad and hard nail is critical for the forming this geometric constraint. As shown in the photo on the right, this geometric constraint is also important in the pressure grasping of everyday objects. For instance, when grasping a small object like cards, tablets, or pens, the use of this geometric constraint allows for a stable and precision grasping. This study demonstrates that our constructed approach found one of the functional rules of the human nail, its ability to generate a geometric constraint in the finger pad. That concludes the research involving artificial fingertips. Next, let me shortly introduce our work on anthropometric robot hands. These pictures show the HDA hand developed by Shu and Todorov in 2016. It replicates the anatomical structure of the human hand, enabling it to grasp a wide variety of everyday objects. Additionally, using leader follower control, it has successfully achieved in hand motion, allowing the orientation of handheld objects to be adjusted without providing any feedback to the operator. In our research group, we gained insight into the development of anthropometric robots by reverse engineering this work based solely on the original paper. While the original study used engineering design finger shape, we took a different approach by using CT CT scan data of actual human bones available in open database and body parts 3D. This video shows the results of our work. We implemented renal flow control using a glove equipped with a bending sensor, controlling 15 joints with 10 sub-motors. The entire system weighs 357 grams. Similar to the original study, the hand was able to grasp a variety of everyday objects. This key, thank you for it. Although not shown in this video off screen, the operator moves their fingers using the radar forward control, and the robot hand mirrors this movement. Through these experiments, we found that it is relatively easy for the robot hand to hold many types of objects placed by the experimenter like this movie. However, we also discovered that in tasks such as picking up objects from a table or transitioning to a tool holding posture are much more challenging. It's very, very, very difficult. So many types of objects can run. Lastly, we also successfully created in-hand manipulation. In this case, the robot hand grasps a very lightweight whiteboard laser horizontally and then adjusted its orientation using only operator's visual feedback control without any feedback. Based on the insight gained from creating this anthropomorphic robot hand, we extended our work to develop various other anthropomorphic robots. The first advancement is the replication of the human wrist joint structure. While many anthropomorphic robots focus only on fingers and hands, our research group has gone further by replicating the wrist structure. We achieved this by the 8 small bones that make up the human wrist with ligaments made by the DeW. As shown in these videos, our robotic wrist can perform 3 types of motions: flexion and extension, ulnar and radial deviation, and formation and spination. Additionally, the fingers are also powered, allowing the wrist to move while grasping some object. We are currently using this anthropomorphic wrist joint robot to investigate the functional roles of the bones of the human wrist. Next, I'd like to introduce our work on replicating the structure of the joint capsule. In conventional anthropomorphic robot hands, the joints were held together by ligaments, and relatively thick rubber sheets are used to simulate the viscoelastic properties of joints. To reduce friction in the joints, we replicate the human joint capsule structure by wrapping a thin wagon film around the bones fixed by ligaments and injecting hyaluronic acid solution. This liquid acts as a lubricant, reducing joint friction. We also found that increasing the number of film layers wrapped around the joint increases joint stiffness, and the more liquid we inject, the lower the joint viscosity. These findings suggest that we can design the viscoelastic properties of joints, which could become a foundational technology for the building diverse anthropomorphic robots. Next, we'd like to introduce our work on replicating the human shoulder joint. This robot mimics the connection between the human humerus and the scapula. In previous studies, this connection was often implemented using mechanical ball joints over thick rubber membrane. However, in our research, we constructed the shoulder joint using ligaments made of wire for the optimal ligament arrangement. In comparison to shoulder joints made from rubber membrane, we found that constructing the joint with wire ligaments significantly reduced the resistance force. We are now expanding this work to include the robotic shoulder joint with movables through the functionality. Finally, let me introduce our work on replicating the structure of the human foot. Similar to our work on the hands, this robotic foot is constructed using bones, ligaments, and tendons. We also include the frontal neuroses, a key feature of the human foot that connects the hip to tooth. We built an experimental setup where the robotic foot was dropped vertically to measure impact force for landing. For comparison, we tested three types of feet: a flat foot, like a humanoid robot, and rigid rigid foot, only a movable joint at the base, and a soft anthropometric foot. Like this movie, we dropped anthropometric foot and measured impact force. The results showed that the anthropometric soft foot was able to absorb the landing impact. So that currently we are developing this robotic foot to enable walking. It's very challenging. Through the development of anthropometric robots like this, we have shown that a constructive approach can help us better understand human motor mechanism. Finally, let me wrap up the conclusion. In conclusion, although there are many challenges, the manual electric shoulder disarticulation prosthesis can substitute for the motion in individuals with bilateral shoulder disarticulation. Additionally, the asymmetrical shape of the human distal phalanx, along with the interaction between the hard nail and the soft finger pad, enhances the precision grasping performance. The key take-home message is the bio-inspired approaches are effective for human body regeneration, functional substitution, while biomimetic approaches are well suitable for human body replication, functional restoration. Finally, I'd like to express my gratitude to my family, collaborators, and all members of my laboratory. Thank you very much. That's all.
Thank you, Professor DeW, for that insightful presentation. The floor is now open for questions.
Sir, actually, this section cleared many of my doubts, but there is one particular doubt which I have noticed. That is basically this entire thing is on neuropsychiatric rehabilitation thing. So when we included anthropometric robots, cyborg, and computational neural science in this aspect, can we integrate virtual reality, robotic assistants, and neural feedback system, that is basically the brain-computer interface, so that it will be useful for many of the people? And in these three, which one will be most useful? And one more thing is, we use feed-forward mechanism, right? Which is basically convolutional neural network, CNN. Why didn't we use feedback approach, that is basically RNN? And
second question is, we not use convolutional neural network. We only
feed forward approach we have used, right?
Yeah.
Which is kind of similar to CNN. So why didn't we use feedback approach?
Feedback approach means what types of feedback approach? It's in the
Like based on the feedback training itself.
Visual feedback for control is very have time delay. So we not use the visual feedback to the user.
And what about the virtual reality robotic assistant and neurofeedback system?
Neurofeedback system, yeah.
Yeah, which one will be more viable to use in this case?
Neurofeedback system is affect brain function but we use only EMG data of which relate to the movement information. Our system not directly affect the brain connection and brain function. But of course, the patients uses the processes. The patient's brain affects the system of the processes, but we don't evaluate. And, it's difficult to evaluate the effect of the system to the brain.
Any other questions? So, sir, in the EMG shoulder disarticulation process, You talked about reducing the visual headroom by introducing adopting learning-based controller, which was like a short path through the visual.
I cannot understand your
So,
question so much.
like you said that you wanted to reduce the work pathway of. Can I come there and ask the question?
Mhm.
Actually, they made the reflexes fast by using that, what you are saying.
Actually, I can't ask on the mic. Visual feedback you are asking? Yeah, how did you cover that gap? Visual feedback you were using that was reducing the processing time. I was asking
What is?
that topic.
Our system uses not fully visual information. Our system uses
He's having problem in speaking on the mic. Come there. The normal pathway was through the eyes, and
yeah.
then you modified it using the that from till here. Like you reduce the path, some learning mechanisms.
That's right.
Yeah.
And I wanted to ask, what technology did you query as a higher level student and would like to
Simplify the screen layer that shall neural network learning EMG data. Not running the visual information. We use the visual information as a text data. It's used to calculate the target position in the system. So we not use visual information with the learning function.
did you
Change. But change. Change.
like you did you did see that there was a normal path which had lots of details. And then you use something to overcome that delay. There's something there which learned.
Mhm.
So I wanted to
Fine approach. Our learning system learn the patterns of the existing interpretation domain, interpretation domain data of the EMG data. So the modify this modify loss of yeah pattern is changed, but the user the dissatisfaction user generate some pattern of corresponding to some move. The learning system run the yeah yeah
not using the normal. How are you learning the pattern?
pattern.
There's something that has to interpret what happened. What the part happened.
Sorry,
Okay, come back, come back.
Yeah,
Put the
I
slide.
think we can discuss it during the high tea.
Okay.
Any other questions? That's all. Thank you, Professor Datogo, for that enlightening session on regeneration and replication of human body. The presentation has given us fresh insights into this important area. Now I'd like to invite the director, Sir Professor Bhatendu Kesin, for presenting memento as a token for appreciation for Professor Datogo. Okay, so it will be Professor Puneet Tandon. Yeah.
आप इस साइड खड़े हो, आप उस साइड खड़े होंगे, लेकिन वो अकेले खड़े हैं, आप खड़े हो।
Thank you, sir. We'll now take a short tea break. Please proceed to the tea area, and we will resume the final session of the day at 3:30 p.m.